on this computer myself, which I've sometimes been late to. Okay, yes, Queen. Yes, that would be great. What makes a presentation good? Again, the stakes are pretty low here because you get full credit even if it's a bad presentation. But to get extra credit, just be creative. I mean, we've had rap music, we've had interpretive videos, we've had just spectacular video productions. The reason I give you full credit for doing it is, it's towards the end of the semester, and it's only 4% of the grade. So I don't want most students to spend an exorbitant amount of time, but hey, if you can do something creative, that's great. This is supposed to be fun. Okay, so let me mute everybody. And any questions before we get started? So today and next Tuesday is all about the universe. So it's very cosmic. And next Thursday is going to be about life in the universe. We got a lot to cover in these, not a lot of math, but just a lot of literally mind-blowing topics. So today we're going to be covering, the Big Bang Theory, but the way I've structured this lecture is in terms of, I'll just do something simpler like time travel and record how the Earth was made. Yeah, that'd be great, especially as a rap music video. I would definitely give you extra credit for that. So if you remember, in previous lectures, I talked to you about dark matter and evidence for dark matter. And I went into detail about 4 lines of evidence for dark matter. And I said there's 3 more, which we'll be covering in a future lecture. Well, this is the future lecture. So today we're going to, we're talking about the early universe, but we're going to structure it around the evidence for dark matter. So let's start with some questions. Make this a little smaller. Sorry. Even with the big screen, sometimes you run out of real estate.
Brent, I don't think you turn on a PowerPoint.
Oh, Jesus, you're right. Thank you. Oh, my God, I just recorded myself saying that word. Thank you for letting me know. It's amazing how often I forget that. Okay, so evidence for dark matter. Remember, I mentioned that 4 lines of evidence for dark matter in great detail. We're covering the other 3 lines of evidence today. The cosmic microwave background, cosmic nucleosynthesis, and the large-scale structure of the universe. These are topics in their own right, but I'm structuring them around evidence for dark matter. Okay. So, thank you for letting me know I was not showing that. So Hubble's law implies A, is infinitely old and getting larger. B, began expanding long ago and has a finite age. C, will slow down because of dark matter. D, has repeatedly expanded, contracted. E, will eventually stop and collapse. This is a repeat of a question from last lecture. Okay, so most you got this right. Began expanding long ago as finite age is one of the most profound discoveries of the 20th century. The fact that the universe had a beginning, and we can tell you exactly when that beginning was. And the universe is expanding and has always been expanding. Now, it is also slowing down because of dark matter, or, well, actually, you will see why it isn't, but that we'll wait for the next lecture. Okay. So, Big Bang.
Our whole universe was in a hot, dense state that nearly 14 billion years ago expansion started.
And the theme song for that show actually has it pretty accurate, although it's more like 13.8, but that doesn't really rhyme. So, here are the lines of evidence for dark matter. We covered galactic rotation curves, galaxy clusters, the bullet cluster, and gravitational lensing in previous lectures. We're covering these 3 now. Remind yourself, I'm just a reminder that our galaxy is rotating faster than it should if the only matter that existed was matter we could see. And so there clearly is matter that extends way beyond the galaxy that must be dark matter. And in fact, the dark matter halo around this galaxy is about 10 times larger than the galaxy itself. The fact that we have clusters of galaxies that seem to be bound to each other, and if the only matter that existed was the matter we could see, there's no way that they could be orbiting each other. There has to be dark matter that keeps the galaxy clusters together. We talked in detail about the bullet cluster, where two galaxies collided and the ordinary matter slowed down, whereas the dark matter, which we detected through gravitational lensing, just kept going, meaning that dark matter, not only does it not interact with normal matter, it doesn't even interact with itself. Gravitational lensing is where we use mass to basically create lenses, and that tells us how massive things are. So if we look at how much gravitational lensing there is in the universe, that tells us how much mass there is. And there's about 10 times more mass than we can see just based on that gravitational lensing, the first 4 lines of evidence. Now we're going to get to 3 other lines of evidence. The first one is the cosmic microwave background. And the cosmic microwave background clusters in such a way that dark matter must have existed in the early universe. And this slide probably doesn't make any sense to you, which is okay, because I'm going to spend the next 5 minutes explaining this slide, and at the end of it, you will understand the slide. So let's just start with a video from our friend Katie Mack, who co-teaches this course and has just written this book, so which is New York Times bestseller. I recommend picking it up. It's great. And no, I don't get a kickback.
Light travels at about 1 foot per nanosecond. Hold your hand up 12 inches from your face. You're seeing your hand as it was a nanosecond ago. Everything you look at is, to one degree or another, in the past. The farther away in space, the more ancient in time. You can't see the sun as it is now, but you can see it as it was about 8 minutes ago. You can't see Alpha Centauri now, but you can see it 4.4 years ago. You see the Andromeda Galaxy as it was 2.5 million years in the past, and so on. With powerful telescopes, we can see galaxies whose light has been traveling to us for more than 13 billion years. We see them shining in a universe that's still young, where gravity has barely begun to pull matter together into stars and galaxies. But we can see something even more distant and more ancient than the first galaxies. If we peer out far enough, in between the galaxies, we can see parts of the universe that are so far away, it has taken the light from that distance very nearly the entire age of the cosmos to reach us. When we look at the most distant parts of the cosmos, in every direction, we see parts of the universe that are so far in the past, they're still in the final stages of the Big Bang. So far away, so far back, space is completely filled with a dense, roiling plasma, the fire of creation. We are not the center of the universe, but we are the center of our own perception as light reaches us from afar. We lie embedded in nesting doll layers of cosmic time. Each concentric sphere is an era, like geological strata, all around us. The most distant layer of time that we can see is the light that has been traveling since the moment the primordial fire began to cool. The cosmic microwave background surrounds us at every edge of our vision. We are embedded in shells of cosmic time, and the final one is fire.
Big thanks to Katie Mack, aka Astro Katie, for collaborating with me on this.
So that fire is the cosmic microwave background. That is the cosmic microwave background, which completely surrounds us, as you saw in the video, is basically the birth pangs of the universe. And let me give you a little bit more detail about that. So here, the universe now is expanding, but let's wind that clock back. If we wind the clock back, then the universe must have started from a very small infinite dot, okay? A dot of infinite density, infinite temperature, and infinitely small. And it's not just the universe, but space-time itself. And then it expanded from there. If it's infinitely hot, it would have a black body radiation that would be infinite, but just moments after that infinity, it would be hot and it would be emitting electromagnetic radiation with a thermal spectrum that we could detect. And as the universe expands, that electromagnetic radiation from the beginning of the universe would cool. And the universe is expanding for so long, it is cooled now so it has an apparent temperature of little under 3 degrees Kelvin. So really, really cold. And so that would peak the spectrum into the microwave region. Okay. And this was theory. People did calculate this in the 1960s, but nobody thought you could actually observe it. Until two guys, which you see standing there, two engineers at Bell Labs in Homedale, actually Crawford Hills, New Jersey, were working on the noise that they were getting from the microwave transmitters that AT&T was setting up across the nation then. Two engineers, and when they looked, they saw that this they were getting distortions. They were getting a signal, not from some terrestrial source, not even from the sun, but from everywhere that they pointed the this microwave radio telescope. And they thought, they even wondered if there was bird poop in the antenna itself that was causing this. Well, it turns out what was causing it was this birth pang of the universe, what we now call the cosmic microwave background. Now, these were engineers, not scientists. They didn't know what to expect until one of them was on a plane trip and was talking to someone that was working in Princeton and knew about the theory that we should see the birth pangs of the universe. And when the engineer, I don't know if it was Arnold Penzias or Wilson, mentioned, oh yeah, we're working on this and we're discovering this microwave background that permeates everything. We don't know what it is. That was the aha moment. And the aha moment gave them both Nobel Prizes. And we'll talk about that in a video shortly. I actually met both of them. My former father-in-law worked for one of them in Crawford Hills. So here's the thing. What we see of the cosmic microwave background, I lied a little bit. It actually isn't the radiation that comes from the Big Bang itself. It comes from 380,000 years after that Big Bang. You can think of it like our sun. Our sun has an energy generation at the core, but we don't see the radiation that's generated there because it has to work its way through the rest of the sun. Okay. And so as it works its way through the rest of the sun, it gets what we call thermalized. It turns into a thermal spectrum that produces that nice shape that you all have grown to know and love. And what we do see is the photosphere, the surface of the sun, not where the energy generation was. And kind of an analogy here is after 380,000 years, the universe became transparent enough that the radiation of that birth pang could escape. And by 380,000 years, it had cooled quite a bit. It was only in the gamma rays. It wasn't in the infinite range. And what happened at 380,000 years were the constituent particles that were making up the soup of the very early universe combined to form atoms. And all of a sudden, the plasma that was opaque to radiation became transparent, and we saw that light. And I'm going to go over this explanation multiple times. So if you didn't quite catch it, don't worry about it. It'll be coming around. This proved without a shadow of a doubt that the universe had a beginning in a Big Bang explosion. Well, it wasn't an explosion. So again, I've showed you this slide before. We're looking back. As we look back in time, we look in earlier and earlier epochs until, and as we look back in time, that light is more and more redshifted until we get to the cosmic microwave background, which was only 380,000 years after the creation of the universe itself. And we're looking back in time so far that it's redshift by a factor of like 1100. And this incredibly hot radiation that emitted from the creation of the universe is now in the microwaves. Okay. So the microwave, when they first discovered the microwave background radiation in 1965, it looked absolutely uniform regardless of where you pointed your telescope. And that created a problem because that implied that the universe was completely smooth at its initial creation. which means we don't exist because the universe would be too smooth to clump together to form galaxies and stars and us. So we really didn't like not existing. And so we assumed that there must be some clumpiness to that initial microwave background, but our instruments just weren't sensitive enough. And it wasn't until the 1992 when COBE went up that we did a very, very careful measurement of the microwave background, and we discovered, sure enough, there is some clumpiness. And how clumpy it is critical for our theories of the way galaxies and stars were created early on. And so this was the first picture. We send up another satellite called WMAP to make an even better picture. And then we did a third satellite called Planck, which gives an even better picture. And this sort of clumpiness tells us just an incredible amount of the very early stages of our universe and how galaxies and stars are created. So the actual Big Bang has basically hidden behind the background radiation, the Big Bang. Yeah, that's exactly right, Ethan. What were they looking for when they originally built the telescope? So Sam, what they were looking for was that at the time, this is before fiber optics, at the time they were trying to do high-speed communications across the nation using microwave transmitters. And in fact, you can sometimes see these microwave transmitters that they're not operational, but they haven't bothered to take them down on top of tall towers. They look like, as you saw, that kind of a cone-shaped thing. And they discovered there was just a lot of noise that was cutting down on their transmission speeds, and they really wanted to know what the source of that noise was. And so Bell Labs says, find out what the source of the noise is, and maybe we can eliminate that noise. And they were just looking to make better microwave transmitters. So too smooth is a way similar to heat death. Yeah, Ethan, I hadn't thought about that, but yeah, that's true, because if the universe is completely smooth, there's no clumpiness to make anything. And if the universe has a uniform temperature, there's no clumpiness in temperature to form any sort of, energy flow to do anything. Yeah, that's a good analogy. I won't get into details about the clumpiness, but that clumpiness tells us an incredible amount about the early universe. And here is a picture as we're zooming out. This is like the picture of the entire universe we showed before, except now we're going to zoom out even more and show that we're centered in this bubble that contains that microwave background, which is the birth pangs of the universe. And just like when you walk through a fog and you're surrounded by a bubble, it isn't that this bubble exists. It is our bubble. And if you move someplace else in the universe, you'll have a different bubble. What is the color key for this image? Don't know. Good question. Certainly, I think red refers to higher density and blue refers to lower density. That's typically what people do. But I don't know for sure. Here's another video on the cosmic microwave background. And I'm going through this in excruciating detail because it's so important.
If you look up at the night sky in any direction, past all the stars and more stars and galaxies and superclusters of galaxies, you will see light that has been traveling for 13.7 billion years to reach Earth. It's the oldest and most primeval light in the universe, a picture of our cosmos in its hot younger years, and it's called the cosmic background radiation. Of course, you can't really see this light with your naked eyes because it's in the microwave band of the electromagnetic spectrum. But it is visible to radios and radio telescopes, and even makes up a small portion of the salt and pepper on an analog TV. Where does this luminescent background come from? Well, just after the Big Bang, the entire universe was still so small it would have been very dense, scorchingly hot, and because it hadn't yet had time to get rough and uneven, it would also have been scrumptiously smooth. For a while, things would have been so sweltering that electrons didn't settle down as parts of atoms or molecules, but instead roamed freely in a kind of red-hot cosmic soup. That soup would have had lots of light bouncing around it too, scattering off of electrons and protons like a hall of mirrors. However, as the universe expanded, there was less and less energy to be had in any one place. And when things had cooled to just below the temperature of the sun, pairs of electrons and protons no longer had the energy to resist each other, and they fell into the electromagnetic embrace we call the hydrogen atom. These electrons were so enamored by their new proton love interests that they effectively began to ignore all the light bouncing around them. So with fewer free electrons for light to interact with, the universe suddenly became transparent, and all the pent-up light was sent forth in whatever direction it had been headed after its last scattering, doomed to travel alone and unnoticed through the cosmos. That is, until it bumps into something solid. When we finally see it here on Earth, this light has been stretched so much by the 13 billion year expansion of space that, like a record slowing down, its frequency and color have shifted from the original sunlight white all the way to cool microwaves. Thus, it's often called the cosmic microwave background radiation, or CMB. And just as we can tell the temperature of a red or white-hot iron from its glow, this light tells us the temperature of empty space, currently around 2.725 Kelvin, or minus 270 degrees Celsius. However, the universe isn't exactly 2.725 Kelvin in every direction. If we look closely, there are small and seemingly random but noticeable bumps all over the place, kind of like milk that's starting to curdle. Our best understanding is that these cosmic curds formed as quantum fluctuations in the otherwise creamy infant universe, and then began to coagulate as the universe cooled and expanded. It's hard to overstate just how small or unbumpy these fluctuations of temperature and density were to begin with. The hot or cold spots were only hotter or colder than their surroundings by a factor of about 1 in 100,000. That's like noticing that a bacteria makes a beach ball bigger. But while this clumping of the universe initially resulted in small variations like the ones we see in the CMB, later on the chunky curds of primordial soup attracted each other gravitationally, and they ultimately coagulated and coalesced to form all of the massive structures in the universe that we see today, like planets, stars, galaxies, and superclusters of galaxies. So when we look up at the night sky past those galaxies and see the ancient light of the cosmic microwave background radiation, we're literally seeing the starting point, the proverbial cream, if you will, from which the starry curds of the universe congealed. Or quite simply, proof that the moon really is made of cheese.
So
To give you a more complete experience of how awesome the cosmic background radiation is,
Brody asked the question, what are the states of matter other than solid, gas, and liquid? Can somebody answer that? Because there's 4 states of matter, not 3. Were hydrogen atoms novel in their state of matter when they first formed? So Brody, at the very beginning of the Big Bang, plasma, that's correct. There are 4 states of matter, solid, liquid, gas, which you learn about in elementary school, but the 4th state of matter, which we see all over the place, is plasma. So for instance, the centers of stars are plasma. Plasma is where you have naked nuclei of atoms and electrons that are floating around. So plasma is very highly electrically charged. And to turn plasma into gas, you need something at temperatures below 6,000-ish degrees. And so it wasn't until the universe cooled down to that 6,000 degrees, it turned from a plasma into a gas. We'll never forget the plasma song. We can see light from the beginning of the universe, but we can't see the edge of the universe. Does that mean that space-time expands faster than the speed of light? Yes, that's correct, Ethan. The observable universe, as we talked about before, is the parts of the universe that we can observe, and there are other parts of the universe that are expanding away from us faster than the speed of light, which means that we in principle can never observe that part of the universe. Just because things are expanding faster than the speed of light, it doesn't violate relativity. Relativity doesn't say things can't move faster than light. It just says you can't transmit information faster than the speed of light. And since we can't see that part of the universe, it doesn't violate that. Previous teacher mentioned the Bose-Einstein condensate. Yes, Brody, boy, that is so far beyond this course. And in fact, it's beyond beginning calculus, quantum mechanical course. You only get that in the advanced courses. So Art, I'll have to talk to you offline. It's a very complicated subject, and we don't really talk about that in this course. So anyway, that clumpiness is what causes the universe, but there's a problem with the clumpiness. And the problem with the clumpiness is if you're dealing with ordinary plasma matter and electromagnetic radiation, which is bouncing around, any sort of clumpiness of that matter will instantly be smoothed out by the bouncing around of the radiation. And so if the universe consisted of nothing but ordinary matter and radiation, the cosmic microwave background would be as smooth as it possibly could be, and galaxies and stars could not have formed. So the only thing that can cause the clumpiness before 380,000 years after the Big Bang is something that doesn't interact with electromagnetic radiation, because it's the electromagnetic radiation bouncing around. It smooths everything out. Okay. Well, what could possibly do that? The only thing that could do that is dark matter. Dark matter clumps in the very early universe, and electromagnetic radiation cannot smooth it out because it doesn't interact with electromagnetic radiation. And it's that clumpiness of dark matter before 380,000 years that attracts the clumpiness, especially after 380,000 years, attracts the clumpiness that creates the stars and galaxies. So the fact that we exist, the fact that this cosmic microwave background is clumpiness, is direct proof that the dark matter must exist. And it's dark matter that created that clumpiness that we see. And that's why that clumpiness of the cosmic microwave background is so, so important. It tells us details about dark matter, and it also tells us details about how galaxies formed. So here we can see initially everything is completely smooth. Then the dark matter starts to clump. Notice that the normal matter doesn't clump. And then eventually the dark matter clumps so much that it now starts to attract the ordinary matter. And this is especially true once molecules form, we have gas, and the electromagnetic radiation escapes and forms what we see as the cosmic microwave background. Okay. So that's this slide, which I showed initially, and you didn't really explain it. Okay, so that's line of evidence number 5. Line of evidence number 6 is Big Bang nucleosynthesis. How were the elements created in the initial Big Bang? And this is complicated, so we're going to kind of go over just at a very surface level. So the Big Bang nucleosynthesis, as I did before, I'm going to show you the slide, which you won't be able to understand, just to show you where we're headed. Where we're headed is deuterium, which is an isotope of hydrogen, was created in the Big Bang, and the amount of deuterium that was created in the Big Bang is critically dependent on how much mass there was, normal matter there was in the Big Bang. Okay, and so the amount of deuterium in the Big Bang tells us how much ordinary matter there must exist in the universe today. Okay. The thing is, that measurement conflicts directly with how much matter must be in the universe. How much matter must be in the universe is this area here, and this is how much matter must exist in the universe today based on how much deuterium was created in the initial Big Bang. And so they conflict. The only way to make this make sense is this is how much ordinary matter there is, and this is how much dark matter there is. And we'll come back to this slide. So let's talk about the Big Bang itself. The Big Bang itself started at time equals 0, and it was infinitely dense, infinitely small, infinitely hot. And then the whole universe expanded enormously in what's called inflation. And that inflation happened over like 10 to the minus 23 seconds. And then it expanded at a normal rate until 380,000 years ago, where the photons were able to escape, and we see the cosmic microwave background, and then we get to today. So here's another graph of this. There's hundreds of different graphs of this. So here we have the initial creation, and some time flows this way. Here we have the initial creation of the universe. We have this enormous expansion of the universe, which isn't really a theory, it's just an observation. The universe must have expanded 1 billion times faster than the speed of light initially. And then the universe consisted of just pure energy. Eventually, as the universe got bigger and cooled down, that pure energy coalesced into electrons and protons. And then eventually, at 380,000 years, those electrons and protons combined to form atoms. The photons escaped. And then we have something that we have not talked about yet called reionization. Reionization happened about 1 billion years later. Here it says 300 million. What's a few hundred million among friends? Where the stars and galaxies started to form, and the radiation from those stars and galaxies reionized all of that gas and turned it into plasma, which is where it is today. Most of the hydrogen in the universe is ionized. is a plasma. But because at that point the universe had expanded so enormously, it no longer trapped the radiation. So we had reionization, and then we had stars and galaxies form, and then we have today. Okay, so this is the history of the entire universe. We'll be going over this, 5 different ways in the next 5 minutes. So the question is, how did these particles form? These particles that formed the elements that we know today formed just from pure energy through Einstein's equation E equals mc squared, where pure energy can create particles and their corresponding antiparticles. Here is the particle zoo. This is our current theory of all the particles that exist in the universe. It looks complicated, but this is incredibly simple compared to the alternatives. And in fact, you can pretty much skip, just for the purposes of this course, skip these 2 columns here, okay? So what the universe consists of is quarks, typically up and down quarks. Forget these quarks. These quarks are just, they're posers. The up and down quarks are the important quarks. It consists of quarks, neutrinos, and electrons. That's it for normal matter. Quarks, neutrinos, electrons. Over here on the right, we have a whole bunch of stuff, this gluon, boson, W boson, forget about those. And we have just the photons. So for normal matter, we got photons, which is light, quarks, neutrinos, and electrons, and then a bunch of other stuff that are hangers on that are related. Okay, and we also have a Higgs boson, which we won't talk about in this course. Protons and neutrons are made up of 3 quarks, and notice they're made up of up and down quarks only. Okay, so that's why these other quarks are just not that important. Atoms are made up of protons and neutrons in a nucleus, and then electrons, which are going around. And then these quarks and electrons are positively or negatively charged, so there's a lot of electrical charges floating around. The quarks are held together not with an electromagnetic force, but what's called a color force, or a nuclear strong and nuclear weak force. We won't be talking about that. But the question is, how did these quarks, neutrons, electrons, and neutrinos form? They formed in the initial Big Bang. The energy, pure energy, created quarks out of energy, specifically out of photons. So at a millionth of a second, which is fairly late in the creation of the very earliest universe, the universe consisted only of photons. So photons have enough energy, 2 photons can bounce into each other and convert into a pair of particles, a quark and an antiquark. And these quarks could eventually, as the universe continued to cool, the quarks would eventually clump together and form neutrons and protons. Okay, so here we've got quarks. So we've got photons during the particle era. Those photons created quarks. Those quarks got together and made protons and antiprotons. So now we have protons, neutrons, and electrons and neutrinos, and they're all just floating around each other, making stuff. During the particle era here, the first protons and neutrons formed. Some of those protons and neutrons clumped together to form hydrogen nuclei. So most of them, 75% of them, were just naked protons and neutrons. But 25% of the time, those neutrons and protons would clump together to form nascent helium nuclei. But then we have the nucleosynthesis era, which starts at 0.001 seconds after the Big Bang. The first protons and neutrons came together to form hydrogen and helium. And then after 5 minutes from the beginning of the Big Bang, that nucleosynthesis ceased. So all of the hydrogen and helium that exist in the universe today, and all the deuterium, which is an isotope of hydrogen, formed in the first 5 minutes. So you have hydrogen and helium and deuterium atoms in your body today. And those atoms were created in the first 5 minutes of the Big Bang. And they're not destroyed, they're not created. They were created in the Big Bang itself. And so after that first 5 minutes, not much happened other than the universe gets a lot bigger and a lot cooler until we reach that big 380,000 years where it cools so much that those neutrons, protons, and electrons get together to form atoms, and we now have the cosmic microwave background. Okay. At 380,000 years, we also call that 380,000 years the recombination event. It doesn't make any sense to me because it's not recombining. Recombining implies that it was combined at some point, and there was never a point where it was combining, but that's just astronomers using language in a weird way. So it's called recombination era, 380,000 years. And later on, we talk about the reionization era, which is like 1 billion years later. So here's the universe. And again, we're going over this multiple ways because this is important information. The very early universe, the radiation dominated. In fact, at the very earliest universe, there was nothing but radiation. And that radiation eventually created the particles that we then see. And then later on, matter dominated the universe. So here we have ionized gas at 380,000 years. We have neutral hydrogen. And then now this graph says 600 million years, where we have the reionization event, where the universe, stars and galaxies started to form, and those stars and galaxies then started to re-energize the universe with very hot electromagnetic radiation, much hotter than the cosmic microwave background, and that reionized this neutral hydrogen. And that happened about anywhere from 300 million to 1 billion years earlier, depending on what author you're looking at. So there's the recombination event. Here's the reionization event. So the important dates in the universe: the singularity, which may or may not have been a singularity at 0 seconds. Inflation, 10 to the minus 34 second. The universe expanded enormously. Again, inflation is just an observation. It's not a theory. We don't know what caused that inflation. Big Bang nucleosynthesis. Hydrogen, helium, and just a fraction of a percent of lithium were formed in the Big Bang itself in the first 5 minutes. Now, lithium then is formed in other nucleosynthesis events in the centers of stars, whereas hydrogen and helium is not. So all the hydrogen and helium that exists in the universe today is primordial. I'm sorry, all the hydrogen. Helium, of course, is created. Some helium is created in the center of stars. We have recombination. Again, the recombination event at 380,000 years, which is the cosmic microwave background, and then the reionization event at 1 billion years. Those are the important days. Well, of course, today. That's an important day, too. Wouldn't it be fun if we rejiggered our calendars to start at t equals 0? So today is 13.77888 billion years. And then, next year would be 13.788877 billion years. Okay. Big Bang nucleosynthesis, Big Bang fusion, hydrogen, helium, and just a little bit of lithium. All of these other elements are created in stars. Okay. So going back to this, one of the things that happened in that first 5 minutes was an isotope of hydrogen called deuterium was created in that Big Bang, and it's not created in any other way, in any other mechanism. So all the deuterium we see must be primordial. And the amount of deuterium that's created compared to the amount of hydrogen and the amount of helium is critically dependent on the density at that time. And if we extrapolate the density that must have existed in the Big Bang to today, that gives us the present day density of normal matter, which is down here. However, based on our measurement of the Hubble expansion number, the density of the universe must be over here, okay? And again, this is a very strong line of evidence for dark matter. So here is what the density of normal matter must be. Here is what the density of overall matter must be. And this delta must be dark matter. So this is line of evidence number 6 for dark matter existing. And only with dark matter does everything make sense. Okay. That brings us to number 7, the last line of evidence for dark matter. At the end of this course, you'd better be absolutely convinced dark matter must exist. Our universe makes no sense without it. Large-scale structure of the universe. Remember that clumpiness in the early universe is a factor of the dark matter creating those clumps. Well, without dark matter, even after that 380,000 years, there's not enough ordinary matter to create the sort of clumps that we observe in the universe. In particular, there's not enough ordinary matter to create this kind of spider webby structure that we observe. Okay, so here is a simulation that consists of normal matter, dark matter, and then we'll talk about dark energy later. And only through the introduction of lots of cold dark matter do we get this sort of clumpiness. Okay, and here's a simulation running. And this is exactly what we see, as you saw in the previous videos, for the shape of the universe that we see it. Our universe, if we look back at the farthest reaches of our universe, it consists of hundreds of billions, if not trillions of galaxies. And those galaxies all seem to align along this filamentary structure. And this filamentary structure is a natural consequence of dark matter clumping together. And what this simulation shows is the left shows the density of dark matter based on the clumpiness of the cosmic microwave background. And over time, dark matter will clump even more and more because it's gravitationally attracted to each other. Over to the right is how the ordinary matter will then be attracted to that clumpiness of dark matter. Remember, there's 10 times more dark matter than ordinary matter. So the ordinary matter is strongly attracted to the clumps of dark matter. And as the ordinary matter clumps on the dark matter, it starts to heat up. And as it heats up, it will form stars and galaxies. And so that's the simulation we're going to run. And here is the time since the Big Bang, right there. Again, the left is showing the clumpiness of dark matter. The right shows the temperature of ordinary matter. And you can see the dark matter is starting to clump higher, harder and harder. And the ordinary matter is clumping even harder. And notice that the ordinary matter is starting to heat up. And as it heats up, it will form those stars and galaxies. Time since the Big Bang, 2.6 billion years. So we're still in the fairly early universe. Remember, we're at 13.8 billion years. And here's the number of stars being formed. Now, what you're seeing is explosions of hot gas by all that star creation and the supernova explosions. So it's only through the clumpiness of dark matter that we get normal matter clump enough to have these very these creation events. And now the universe is filled with ordinary matter galaxies, really hot, super ionized, but very, very rarefied plasma that permeates the universe. Okay. So that was line of evidence number 7. So now we have it, the 4 major lines of evidence, and any one of these essentially proves that dark matter must exist. So I hope you're all convinced. So what is dark matter? We have no clue, okay? All we know is that dark matter it has mass, so it's like some sort of matter, but it's no matter that we know anything about. And it doesn't interact with electromagnetic radiation. It doesn't interact with normal matter. It's completely dark. It's completely transparent. You can see through it. It permeates everything. The only thing we know of it is it has mass, and it's got to be what we call cold. Because if it was hot, if it was moving very quickly, it wouldn't clump. And so we know the universe must permeate with cold dark matter. Is it a force? It is a particle? We don't know. Okay. So right now, is dark matter everywhere? Well, yes and no. As you saw in that simulation, on the largest scales, yes, it's everywhere. But on the smaller scales, it clumps a lot. We have dark matter. We have galaxies that are 100 times more massive than their ordinary matter, and we have galaxies that have essentially no dark matter in them. So it's all over the map. And the only reason we know where the dark matter is through gravitational lensing. That's really the only way we can detect where the dark matter is. And so certainly some dark matter is permeating you right now, and you don't know it because it doesn't interact with you. It's kind of like the Positarians. The Positarians is a religious belief, and the Positarians believe that there is a completely transparent, invisible, undetectable floating spaghetti monster out past the orbit of Jupiter. Okay, and they can believe that all they want, but it's by definition undetectable. But they believe in it, so hence they're Positarians. So there's hundreds of experiments looking for some sort of sign of dark matter. They all assume that dark matter must interact with ordinary matter or electromagnetic radiation very rarely, because if it just plain didn't interact at all with either one, I don't know how we could ever figure out what it is. But so we have hundreds of experiments on the ground, and we have dozens of experiments in satellites that are in space. So let's finish up with some questions, and then I'll be open up for comments. In the first few minutes after the Big Bang, A, the universe cooled and formed neutral matter. B, the cosmic microwave background radiation was released. C, electrons combined with protons. D, hydrogen fused into deuterium and then helium. E, the universe was governed by one united superforce. Isn't that the Fantastic Four? Or no, I'm sorry, it's the X-Men. Sorry, X-Men. I always get those two mixed up. So this is a confusing question. So all of these statements are true. It's just when are they true? And so the most important thing on this question is it's asking about the first few minutes after the Big Bang. Do we know enough about dark matter where humans can use it to our advantage? No. I wish we did. How do galaxies without dark matter differ? So Brody, they differ because, first of all, their rotation curve doesn't have that flatness that you see with galaxies that have dark matter. And the number of galaxies we've discovered without dark matter is like 1 or 2. It's not very many. Praise the, FSM. Can normal particles decay into dark matter? Hannah, we don't know. If they did, boy, that would just be a breakthrough. How does dark matter interact with black holes? So Blake, we don't know. Best guess is dark matter interacts with black holes in the same way that ordinary matter does, that it would fall into the black hole and make the dark matter more massive. But honestly, we just don't know. It would be very interesting, wouldn't it? Because again, black holes aren't really an ordinary matter phenomena. They are a phenomena of space-time itself. And everything we've seen suggests that dark matter does follow the rules of space-time. It is gravitationally, it does follow the lines of gravitational force. So I'm going to end this poll. And the correct answer is D, because the universe cooled and formed neutral matter. That happened in 380,000 years. Cosmic microwave background, same time, 380,000 years. Electrons recombined with protons. Yeah, that never happened. I mean, it depends on what you mean by recombined, but typically it doesn't mean that electrons combine with protons. The only time the electrons combine with protons is under intense energy, density, and pressure, where they form neutrons, hence neutron stars. The correct answer is D. What's FSM, by the way? Okay. The cosmic microwave background is Flying Spaghetti Monster. Yes, all hails Flying Spaghetti Monster. So here, the cosmic microwave background, the CMB, is A, evidence supporting the Big Bang, B, proof that the universe is getting warmer, C, a result of a hot intergalactic gas between clusters, D, the observable form of dark energy, E, released from the first generation of stars in the universe. And the correct answer, of course, is A. The CMB, the COBE data showed that with very minor variations, the temperature of the background radiation is exactly A, 37 degrees Kelvin, 4.8 degrees Kelvin, 2.7 degrees Kelvin, 1.4 degrees Kelvin, 0.23 degrees Kelvin. And the answer, of course, is 2.73 degrees Kelvin. So here is the 7 lines of evidence: the galactic rotation curves, galaxy clusters, the bullet cluster, gravitational lensing, the cosmic microwave background, the clustering of the cosmic microwave background, the deuterium abundance, and the large-scale structure of the universe. And that's it for today's lecture. I'm open for questions. Feel free to turn on your mic and we'll have a discussion. And don't forget your project due a week from today. What would be the implications be if nuclear synthesis occurred past 5 minutes? Like, what if there were more matter in the universe? So Brody, I don't know if anybody's done that simulation, but that would be very interesting to do. What I think would be interesting is perhaps if the universe had more or less mass, we wouldn't have the clumpiness to form, or just the right amount of clumpiness to form galaxies and stars. And that would be kind of a selection effect, because we're in the universe that had just exactly the right amount of mass to form the clumpiness to form us. And if it was any different, we wouldn't be here to have this discussion. But yeah, I don't know of anybody that's run that simulation. That would be interesting. I know this somewhere, but the project is being submitted through Zoom recording, correct? So Blake, you can do whatever you want as long as I get a video file that I can upload to YouTube. So if you want to shoot yourself with a video camera or your iPhone, if you want to do an interpretive dance, if you want to, I think PowerPoint has the ability to record a voiceover, and you can send me that file with the PowerPoint. Do anything you want as long as I have an under 5-minute video file that I can upload to YouTube. Any way you can get a video recording, that's correct. I'll send another reminder note, but by far the easiest way to do it is just go to the Zoom yourself, or if the partner, if it's more than one of you, bring up your slides, do share screen of the slides, turn on record, say record on this computer, and then when you're done, send me that video file. That's by far the easiest way to do it. Is it possible as technology advances, we create our own black holes? So Sophia, short answer is no. The reason why is black holes that are less massive than the Earth have densities that are 20 orders of magnitude greater than nuclear density. And there's just no conceivable technology or even physical rules that would enable us to create something that dense. The only way that we can think of that those black holes could have been created is in the Big Bang itself, where all bets are off. We have infinite density and temperature. And those, what we call primordial black holes, would have evaporated by now. What are your thoughts on the multiverse theory? Do you believe there could be other universes? So yeah, that's a really good question. The problem with the multiverse theory is one definition for science is you make a statement that is in principle disprovable. So I say there is a flying spaghetti monster past the orbit of Jupiter. And you say, well, why don't we send out some probes and take a look at it? And I says, no, you can't do that because it's completely invisible and it can't be observed in any way. I am not making a scientific statement because my statement isn't falsifiable. Whereas if I says, yeah, why don't we go out and send a probe and see if there's a flying spaghetti monster? I made a scientific statement. There's a flying spaghetti monster past the orbit of Jupiter, and it can be validated or it can be invalidated just by observation. The problem with multiverse theory is it's not clear that it can be invalidated. Certainly I can believe that there's multiple universes, but can there ever be evidence for or against multiverses? I don't know the answer to that. Certainly there's one UNC professor who believes we can find evidence for other multiverses that do interact weakly with our universe, and she claims that she has actually found that evidence in one corner of the cosmic microwave background. I am not that level of cosmologist, so I can't say whether this theory has any traction or not. All I know is I haven't heard anybody else espouse the theory, and unfortunately there's hundreds of multiverse theories floating around here, and if I hadn't heard any more about this one, I just don't know. So, just because there's no scientific evidence for or against doesn't mean it's not an interesting question. And in fact, we tend to call questions where we can never in principle have evidence for or against metaphysics. And so the difference between metaphysics and philosophy and religion is they're actually, those three words pretty much mean the same thing. So for instance, a metaphysical question could be, does the universe exist for a reason? It's not clear that we would ever have evidence for or against. And so we call that a metaphysical discussion. What will you be researching next or want to research next? Well, I'm of the age, Brody, thanks for asking, where I'm mostly just writing stuff. And so right now I'm making a very extensive course on becoming spacefarers, how we're going to colonize the solar system. And I'm spending a lot of time on this. I'll be presenting that first at Duke next semester. And I think I'm just going to turn that into a book because I think it's a fascinating topic. So really our future is in the solar system and in space, and we should start preparing for that. Yeah, best of luck. Yeah, it's a multi-thousand-year journey. Other questions? I'm open for anything. What do you think of the idea of making floating colonies on Venus? Yeah, so there's a lot of talk about that, especially since the discovery of amino acids in the atmosphere of Venus. And if you look at the engineering and science of it, there's really nothing that would prohibit us from having floating colonies on Venus. But I was watching a video recently, and it's kind of like, why? So you accidentally drop something overboard on this floating colony of Venus. It's gone forever. It goes down to something that is literally hell. It's an interesting idea, but there's other places in the universe where we have solid bodies, like the asteroids, like Mars, like Enceladus, like Titan. That would be a lot more amenable to life. But yeah, there's nothing physical or engineering that would bar us from doing that. Yeah, so Sam, you're right. It's closer. It does have better gravity. It has protection from radiation. Yeah, when you put it that way, you're right. It does have the protection. It does have the right gravity. Here's a problem that we have as we colonize the universe. We have a lot of experience with 1G in terms of its interaction with the human body. We have a considerable experience with 0G. We've had probably decades of life of the various astronauts and their experiences with 0G. And we know that 0G is really bad for long-term survival. Really, really bad. People have survived for a year or so in space, but their body has suffered because of it, even though they exercise 2 hours a day. We have zero experience with partial gravity. So the question is, does 0.38 G, such as we have on the surface of Mars, is that sufficient to get rid of all of the nasty consequences of 0G? Is 0.16 G, which is the gravitational force we have on the surface of the moon, is that going to be sufficient? We have zero experience. And the answer to that question is critical for what happens to life as we try to expand our presence throughout the solar system. I mean, if the answer is that you really have to have full gravity, well, that's interesting and really kind of bad. So pretty much you're stuck with floating cities on Venus, on rotating asteroids that you can rotate at 1G, or genetically modifying the human body so it can withstand lower gravity regimes. How long did it take to publish your book on color? Allison, that's an interesting question. Nobody's asked me about that. It took me 6 weeks to write it because I was writing it 100 hours a week, and I was also trying to finish up my PhD, and I was doing my first startup company, which became wildly successful. So I was under a real time gun, but the second edition of that book took me 3 years. So, uh, yeah, that's a good question. I know I've spent a lot of time with Katie as she published her book, and the way she did it was as she woke up early and she spent an hour every morning just working on the book, and that just to get a book done just requires that kind of, no matter what else is happening, you got all these high priority events that are screaming for your attention. You just break out and write the book. So it's tough. What did you change? I just updated it. No big changes to it. What are the names of the books again? I'll bring them up. So, oh, wow. Look at that. It's no longer on Amazon. I'm so upset. Yeah. Huh. Well, at least it's in the Springer Guide. Free preview. So there's the textbook. I guess you can still buy it, just not through Amazon. That's so disappointing. Wait a second. It's listed in Amazon. Oh, there it is. Just doesn't have the preview. I also wrote a book called the Data Handbook. So look at that. Something interesting when you're a publisher of books that aren't terribly popular is that they show up on Russian websites. So if you want a free copy, you can go to a Russian website and you get the entire PDF available to you. It's too old a book to make a comment. So what was the name of your startup company? So my first startup company, I started 2 companies, was called Spyglass. I started that at Illinois. Spyglass published the world's first internet browser called Mosaic. And so for a time in the mid 1990s, it was an incredibly wild ride. We were the first internet IPO. We went out 5 weeks before Netscape. By the way, Netscape had stolen our technology and we sued them and won. So every copy of Netscape's browser that was sent out, we got a royalty from. Our company produced the first version of Microsoft Internet Explorer. So until last year, the About dialog had our company listed as the creator. Yeah, so you invented Mosaic. No, I did not invent Mosaic. My company did not invent Mosaic. We were the publisher of Mosaic. The University of Illinois invented Mosaic and we published it. But certainly the people that did invent Mosaic came over to our company after we acquired the licensing. Netscape stole the technology from the University of Illinois, and both we and the University of Illinois sued Netscape and won. By the way, the name of the company was Mosaic Communications, and we forced them to change the name. That's why they're known throughout the world as Netscape. What was the name of the other book? The name of the other book was the Data Handbook. Let's see if that one's listed. Oh yeah, there it is. So again. So that was a lot of fun book to write. So yeah, I'm not crazy about Netscape either. It's funny. I've never met Mark Andreessen, but he certainly knows about me. His opinions of the University of Illinois and my previous company are not kind, and our opinion of his is not kind. Okay. Other questions? Yeah. So I had kind of a colorful history before I came back to academia and taught you guys. This is more fun than I've had for a while. Yeah. Are you a UIUC grad? What do you think of Oracle? Yes, I'm definitely a UIUC grad. All of my degrees are from the University of Illinois, Urbana-Champaign, Harbor of the Midwest. No real opinion on Oracle. You should write a biography. Yeah. By the way, I in the early days, in the 1970s, I worked on a computer system called Plato, which became famous in its own right. When I worked at Plato, I also wrote the world's first interactive flight simulator. Somebody that shared an office with me is a guy called Ray Ozzie, who until recently was the president of research and development at Microsoft. Interestingly, he also developed something called Lotus Notes, which was a direct ripoff of the technology that we had developed at Plato in the 1970s. And so there's echoes of the system we developed in the 1970s, even today in the internet, and the way that email is handled in the internet. So it's been quite the journey. Anyway, I'm glad to be with you guys, and I'll see you guys on Tuesday. Thanks a lot. Yep.
Thanks,
You all have
Brandon.
a great day.
I hope you have a great day.
You too, guys. Thanks.